Welcome to an introduction to real analysis. We are going to go through this section by section, continuing here in Chapter 1, Section 2, the set of real numbers. We're going to begin this section by simply stating that the real numbers are, in a very concrete sense, the only complete ordered field. We introduced this terminology in the previous section. This is a result we're only going to state without getting into the proof of, because it's not the focus of this course. The central objective of this section, however, is to begin proving things with suprema, infima, and in general bounds on sets. For example, the Archimedean property is fairly intuitively straightforward. No one ever doubts that it's true, but we want to take care to prove it rigorously using these new definitions. We're also going to introduce notation for unbounded sets having suprema and infima that we call infinite. So moving on, we finally get to the real numbers as a number system. To simplify matters, instead of constructing these formally out of the rational numbers, beginning with the integers, beginning with the naturals, and so forth, we just are going to state their existence. And here it is. There is a unique, complete ordered field containing the rational numbers, and we call this unique, complete ordered field containing the rational numbers the real numbers. Uniqueness here is up to what is known as isomorphism. This is an algebraic notion that we're not going to get into. Note that the real numbers are essentially by definition a complete ordered field. So we're not going to justify why the real numbers are complete or ordered or a field. It is by definition the unique complete ordered field that contains the rationals. Also, the natural numbers are a subset of the rational numbers. Now we've seen that 0 is less than 1. Good for us. Now by induction, you can therefore prove that every natural number is bigger than 0. Now, depending on your convention whether the natural numbers begin with 0 or not, you would want to exclude that. It then follows, again, this is just an exercise, that for any natural number, possibly excluding 0, if that's where you consider the naturals to begin, then for any two natural numbers m and k, so that m is less than k, you can divide by a natural number, this is why you have to exclude 0, and preserve the inequality. Now, a lot of analysis consists of proving various inequalities. So the following proposition is a nice illustrative example. So here is a slightly modified version of proposition 1.2.2. If x is bigger than or equal to 0, and for any positive epsilon, you have that x is less than epsilon, then x must equal 0. This is a very important result. It states if a real number is not negative, but it is less than every positive number, the only choice is for it to be 0. So let's prove it quite quickly. Assume to the contrary that x is not 0. Well, since we already assumed it was bigger than or equal to 0, if it's not equal to 0, it must be positive. But you can then divide by 2 and preserve the inequality. So x over 2 would have to be smaller than x, but still bigger than 0. So simply choosing x over 2 to be epsilon, we contradict the fact that x is less than every epsilon, because it's bigger than x over 2. What the previous proposition really means for us is that there's no such thing as the next real number, at least as far as our standard ordering of numbers goes. More specifically, if a and b are any two real numbers, let's go ahead and assume that a is the lesser and b is the greater, there's always going to be some real number c that you can find in between the two of them. So there is no choice of b that is the next number after a. There will always be something else in between. So for example, you can simply take the midpoint, a plus b over 2. So there is no such thing as the number that comes after a, because you could find a c in between it. But c can't be the next number after a. You can find something in between a and c, and so forth and so forth. So again, let's talk about completeness. The most useful property of the real numbers in this course is not just that it's an ordered field, both of which are very important, but that it has the least upper bound property. Essentially, we want rational numbers. Those are easy to work with and define. But we want to be able to take suprema and infima of any bounded sets, and the rational numbers do not have this least upper bound property, as we've already seen. So we take the rational numbers and we add this least upper bound property, aka completeness, onto it, and that's what the real numbers are. Has the rationals, has the ordering, has the field properties, but then we also put on this least upper bound property. So we've already mentioned that the real numbers contain elements that are not rational, but we haven't actually proved it, so let's do that now. We saw there is no rational number that is the square root of 2. So now what we will show is that there is a real number that is a square root of 2. So in this example, let's show there is a unique positive real number whose square is equal to 2. Let's build a set. It's a set of real numbers. It's the real numbers whose square is less than 2. This is not an empty set. For example, 1 is a real number whose square is less than 2. So A is not empty. However, 2 squared is bigger than 2. Working with our ordering on this field, we now conclude that anything whose square is less than 2 must be less than 2. So it's bounded above. Okay, now I'm not claiming that 2 is an optimal choice of an upper bound or a least upper bound, merely establishing that this set, numbers whose square is less than 2, has an upper bound. Now that it's bounded above, it must have a supremum. Because the real numbers are complete, bounded sets have suprema. Denote the supremum of A as R. So now we're going to show two things about this number R. First, its square is bigger than or equal to 2, but also its square is less than or equal to 2. All right, so we have our set, the real numbers whose square is less than 2. We showed it was bounded above. We defined then its supremum as R. Okay, 1 is in the set, and R is the supremum of that set. So R is definitely bigger than 1, bigger than or equal to 1 at least, therefore positive. Now, if R squared was less than 2, then 2 minus R squared would be positive, and therefore you can divide by a positive number, aka 2R plus 1, and remain positive. So now we can pick some number h that is in between 0 and this fairly arbitrary looking quantity, 2 minus R squared, all divided by 2R plus 1. So under the assumption that R squared was less than 2, we find this h. Since h is positive, if you add it to R, you get bigger. So remember that R was the supremum of the set A. So R plus h is now bigger than the supremum of a set. So what have we done so far? We started with the set A, the real numbers whose square is less than 2. We showed it's bounded above. It has a supremum, therefore. We called it R. We want to show that R squared equals 2. So let's assume for the moment R squared is less than 2. We're hoping to derive a contradiction. Now, since R squared is less than 2, 2 minus R squared is positive. However, the supremum of this set must be at least as large as 1. So 2R plus 1 is also positive. That makes this a positive number. So pick an h, which is positive, but less than that. Also, since h is positive, R plus h must be bigger than R. It is totally free to assume that h is less than 1. If this quantity here is less than 1, then h being less than it automatically makes h less than 1. If this is bigger than 1, you can just replace this with a 1, pick an h in between 0 and 1, and this will still be true. So it's totally fine to assume h is not just less than 2 minus R squared over 2R plus 1, but h is also less than 1. Now we just do some basic algebra. R plus h squared is R squared plus h times this quantity. However, h is less than 1 and h itself is positive, so this product is less than this product because h is less than 1. Also, h times 2r plus 1 is less than 2 minus r squared. The r squareds cancel. This overall is less than 2. So r plus h squared must be less than 2. But since r plus h squared is less than 2, it must belong to the set A, because A is the set of everything whose square is less than 2. So now r plus h belongs to A, but r plus h is bigger than r. So this is in our set, is bigger than this number, meaning r is not an upper bound of A. That contradicts that r was the supremum. Okay. So starting from the assumption that r squared was less than 2, we got this contradiction. Therefore, r squared cannot be less than 2. It is bigger than or equal to 2. So where are we? We have the set A, real numbers whose square is less than 2. We know it's bounded above, therefore it must have a supremum. We called that supremum R. We've already established r squared can't be less than 2. Now we want to show it can't be bigger than 2. Under the assumption that r squared is bigger than 2, we're going to do something pretty similar to the previous slide. We're going to find a positive number h so that r minus h is still positive, but r minus h squared is bigger than 2. We're going to use that to establish that r is not the smallest possible upper bound of A. This will contradict that it is the supremum, the least upper bound. So r is at least as big as 1. 1 does belong to the set A. 1 squared is actually less than 2. And the supremum of a set must be bigger than or equal to every element of it. So now, let h be a real number that satisfies this inequality here. Since r squared is bigger than 2, this numerator is positive. Since r is at least as big as 1, this denominator is positive. So we're going to pick a positive number less than this quantity. We can also make it less than 1, and we can make it less than r itself kind of for free. Just pick r to be a positive number less than 1 and this and r. Now we do basic algebra. Expanding out r minus h squared, you get this r squared, this minus 2rh, but you get a plus h squared. Now h squared is bigger than 0, so we can just say this is bigger than r squared minus 2rh. From this inequality here, 2rh is less than this, so minus 2rh is bigger than 2 minus r squared. The minus r squared cancels here, and you're left with just the 2. So since h was less than r minus h is positive, but r minus h squared is bigger than 2, so r minus h does not belong to the set A. Okay, so we have our set of numbers whose square is less than 2. We denoted the supremum as r. Under the assumption that r squared was too large, we were able to find something that isn't in the set, but is still positive. But now suppose you have any positive number that doesn't belong to the set A. Pick something larger than x. If you simply multiply this inequality, y is bigger than x by itself, because the inequality only involves positive numbers, you can do this without flipping anything around, you get that y squared must be bigger than x squared. Since x didn't belong to A, x squared is at least as big as 2. Therefore, y squared is bigger than 2, so y doesn't belong to A. In other words, if x is positive and not in A, everything bigger than that must also not be in A. So nothing in the set A can be bigger than x. So x is an upper bound of A. And what we have done is, under the assumption that r squared was bigger than 2, we found a positive number, r minus h, which isn't in A. Therefore, it must be an upper bound. But if r minus h is an upper bound of A, that's something smaller than r, which is an upper bound. But remember that r was the supremum, the least upper bound. So we've contradicted the fact that r was the supremum of A. So we've shown both that r squared cannot be less than 2 and r squared cannot be bigger than 2. So r squared must equal 2. Great, we've shown that this set A, as defined, must be bounded, has a supremum, its supremum squared must equal 2. But the claim was there is a unique positive number whose square is equal to 2. Suppose you have another positive number not equal to this r. By the trichotomy law, which states that any two real numbers, one of them is bigger than the other or they are equal, since we've assumed s isn't equal to r, either s is less than r or r is less than s. But in the first case, if s is less than r, then s squared must be less than r squared, and r squared equals 2. So s squared cannot equal 2. And the second case is similar. Okay, so there cannot be another positive number whose square is 2. The trichotomy law and basic facts about multiplying inequalities by one another establishes that there can only be a single positive real number whose square is 2, and we managed to construct it. Okay, so there is only one positive number whose square is 2. Good for us, we can call it the square root of 2. So, the square root of 2 is not rational. We already showed that. The set of real numbers which are not rational is called the set of irrational numbers, and we just showed it's not empty. There is a number whose square is 2 that isn't rational. Awesome. We will show that not only is the set of irrationals not empty, it's actually quite large. So using the same technique as the previous example, you can show that x to the 1 over n exists for all natural numbers n except possibly for n equals 0, and x being positive. So you can take roots of positive numbers. So for any r, which is positive, there is a unique positive real number x so that x to the n equals r. So the real numbers contain lots of numbers that are not of this form, but generally this is a way to construct numbers that must be real but are not rational. Okay, for certain choices of r. I mean, of course, x to the third equals 8 has rational solutions, but x to the third equals 7 does not. Okay, so you can construct numbers that are real but are not rational using this technique. It is not the only way to do so, and it's definitely not going to account for all of the irrational numbers. Okay, on to a fairly important result, the Archimedean property. So we've seen there are lots of real numbers in any interval, but there are also lots of rational numbers in any interval. So the following is going to be a pretty fundamental fact that we're going to rely on a lot in the early sections to prove facts about real numbers. Okay, there are two parts to the next theorem. They're actually logically equivalent. It doesn't seem like it at first, not necessarily. Here we are, theorem 1.2.4. We're going to set it up a little bit before getting to the actual statement that appears in the text. The set of natural numbers is not bounded above. This is pretty intuitively obvious. If you start listing out 1, 2, 3, 4, 5, and so forth, you tend to not think of it as being bounded above. But actually proving it can be tricky to beginning students. So assume to the contrary that the set is bounded above within the reals. Since the reals are complete, we can therefore assign it a supremum, call it alpha. So alpha minus 1 is less than alpha, so alpha minus 1 is not an upper bound. If alpha minus 1 is not an upper bound on the natural numbers, there's a natural number bigger than alpha minus 1, meaning n plus 1 is bigger than alpha. But n plus 1 is a natural number, because n was. So this n plus 1 is also a natural number, which is bigger than alpha. That contradicts that alpha was an upper bound on the natural numbers. Okay, so let's talk about that proof. Here is a pretty common error that I see students make if you ask them to prove the statement natural numbers are not bounded above. They'll say for any natural number, n plus 1 is also a natural number, which is bigger, so n can't be an upper bound, therefore there are no upper bounds. Now, what that actually shows is that the natural numbers are not going to be an upper bound on themselves. There's no natural number that's an upper bound on n. What we had to do was establish there isn't a real number, which is an upper bound on n. And if you look at the inset proof, that's where alpha comes in. The supremum of the set of natural numbers, if it were bounded above, would exist, and we call it alpha. It's real, but not necessarily natural. Okay, and we ended up with a contradiction. It doesn't exist, but that's the sort of crucial twist on this proof. You can't just prove that natural numbers can't be bounds on the natural numbers. You have to show that real numbers can't either. Okay, it's worth pointing out that you can define certain number systems in which the natural numbers are bounded above, just not with the reals, not with an ordered field containing the rationals. On to theorem 1.2.4 proper. First, if x and y are real numbers and x is positive, then there must be a natural number n so that n times x is bigger than y. Loosely put, no matter how small x is, as long as it's positive, if I multiply it by a big enough natural number, that will be bigger than whatever I had picked as y. The second form of this result, if x and y are two real numbers and x is less than y, then there is in fact a rational number, r, in between them. So in between any two real numbers, there must exist a rational number. Let's prove it. First, the first statement. So recall our preliminary result. The natural numbers are not bounded above. So for any real number, that's not an upper bound, meaning for any real number, there is a natural number bigger than that. So since x in the first version here isn't 0, it's positive, y over x is a real number. Since it's a real number, it's not an upper bound on the naturals. Pick a natural number bigger than it, then multiply by x, which is positive, so it doesn't flip the inequality, and you get that n times x is bigger than y. Now let's look at the second result. X and y are now two real numbers, and we've assumed that x is less than y. Now, without loss of generality, we're going to assume that x is actually positive. So without loss of generality is a phrase that gets used a lot in proofs, and it's generally unclear when you are or aren't allowed to say it or use it. That ambiguity never really goes away, no matter how experienced you are. Anytime you see the phrase without loss of generality, you should kind of prick your ears and eyes and pay attention and look for flaws. So generally what the phrase without loss of generality means is there are lots of cases and they are all handled identically. Another way it can be used is we're about to make an assumption that doesn't really change any of the coming arguments. So here what we mean is there's lots of cases and they're going to be handled similarly. So we're assuming for part 2 that x is positive and therefore y is bigger than that. So these are two positive numbers. The other cases would be what if they're both negative, what if one of them is 0, and so forth. So specifically for this result, why is x being positive actually without loss of generality? Suppose x was negative, but y was positive. Then you can simply pick 0, a rational number, in between them. Great. So if one of the numbers is positive and one of the numbers is negative, there's really nothing to prove. If they were both negative, multiplication by -1 would simply transform this into an inequality involving positive numbers. So if I can find a rational number in between these two, then I can find a rational number in between these two by undoing this step. Okay, so if you can prove it for positive choices of x and y, then the proof for negative ones is just a simple little twist and doesn't really change anything. That's what we mean by without loss of generality in this example. So let's just prove it under the assumption that x is positive. So let's make the following diagram. Suppose 0 is less than x is less than y. So here they are on the real number line, 0, then x, then y. What we want to do is show there is some n so that the length of the interval from x to y is bigger than 1 over n. So whatever that distance is of y minus x, we want it to be larger than 1 over n. Now we'll consider all possible rational numbers that have denominator n, 1 over n, 2 over n, 3 over n, and so forth. We'll show that at least one of them has to land in this interval. Okay, so k minus 1 over n to the left of x, k over n to the right of x. We'll show that k over n is actually also less than y. Okay, that if you start listing out your rational numbers of denominator n, you will be to the left of x and then you won't. And this first thing to the right of x will still be to the left of y. That's our idea here. Okay, so assume that x and y are both positive, x is less than y. So y minus x is positive, just subtract x from that rightmost inequality. By the first version of the Archimedean principle, there is some number n so that n times 1 is bigger than this real number. Given any two real numbers and one of them being positive, there is an n so that n times the positive is bigger than the other. 1 is positive, so eventually, for large enough n, n times 1 is bigger than this real number. So now we reciprocate this inequality to obtain that y minus x is bigger than 1 over n. Great, we found that there must be an n so that 1 over n is less than y minus x. So we picked our n, 1 over n is less than y minus x. Now define the set A to just be 1 over n, 2 over n, 3 over n, and so forth, but only those natural numbers over n that are bigger than x. Okay. Now from the Archimedean principle, we know that eventually m times 1 over n will be bigger than x. Again, something times this positive number will be bigger than whatever we want. So something times this positive number will be bigger than whatever we want. So there are definitely choices of m that make this true. So the set A is not empty. Okay, so our set A, rational numbers with denominator n bigger than x, is not empty. The well-ordering principle, which is equivalent to the axiom of induction, this is something hanging around in the background, states that any set of natural numbers that isn't empty has a smallest or least or minimal element. So let's choose k to be the smallest element of this set, the smallest natural number, so that it over n is bigger than x. So k is in this set, but k minus 1 is not. That means that k over n is bigger than x, but k minus 1 over n isn't bigger than x. So here's the inequality we have. We have a choice of k, so that x is to the left strictly of k over n, but it's bigger than or equal to k minus 1 over n. Now suppose k over n was bigger than or equal to y. Then you could establish the following, that this k over n is bigger than or equal to y. Y was already assumed to be bigger than x, and we had above here that x is bigger than or equal to that. Now what's the distance between these two numbers? You would obtain that y minus x, well, y is less than or equal to that, and x is bigger than or equal to that. So when you multiply this by a minus 1, the inequality would flip. Negative x is bigger than or equal to. So y minus x would be less than or equal to k over n minus k minus 1 over n, therefore 1 over n. This is also just stating that the distance between these two numbers, k minus 1 over n to k over n, is definitely 1 over n, and these are in between. So the distance from y to x would be less than or equal to 1 over n, contradicting how we picked n to begin with. So what do we have? We have that k over n was to the right of x, but could not be bigger than or equal to y. So k over n is a rational number strictly in between x and y. This completes the proof of item 2. Okay. So for any two real numbers that aren't equal, we can find a rational number in between them. That's the second form of the Archimedean theorem. We immediately move on to a nice little corollary. The set 1 over n, here the natural numbers are definitely not including 0. So 1, 1/2, 1/3, 1/4, etc. The infimum of this set is 0. So it's certainly not an empty set. It's also bounded below, definitely by 0. Okay, so 1/2, 1/3, 1/4, these are all positive numbers. So 0 is a lower bound. Therefore, it has an infimum. It's a set of real numbers, not empty, bounded below. It has an infimum. So let's denote it as b. b is now the infimum of the set 1 over n, where n runs through the natural numbers, excluding 0. Okay, set b to be the infimum of this set. Since the set is bounded below by 0, and b is the biggest possible lower bound, b is definitely at least 0. Suppose, however, that b was not 0, so it's bigger. By the second item of the Archimedean principle, since b is positive, and I can put a 0 here, there must be a rational number somewhere in between. For any rational number, it will, have a numerator and denominator. You can set the numerator to 1 and make it even smaller. You'll end up with a 1 over n that's less than b. Okay, whatever r is, the rational number given by item 2, this numerator k is at least as large as 1. And that's what this inequality here says. So under the assumption that we called this infimum b, if we made it, we assumed it, to be bigger than 0, we were able to find a 1 over n less than b. But now look at what b is defined to be. It's the infimum of all 1 over n's. So some 1 over capital N can't be less than a lower bound on the set of all possible 1 over n's. So having assumed that b was positive, we contradict that it's even a lower bound. Therefore, b can't be positive, but since it was definitely bigger than or equal to 0, because 0 is a lower bound and the infimum is bigger than or equal to any particular lower bound, we conclude that b must be 0. Okay, so we now have a nice concrete proof of the infimum of a set being a particular number. It's also worth pointing out this set does not include 0, but the infimum is still 0. So how do you use suprema and infima? They're compatible with a lot of algebraic operations once you properly define these operations as working on sets. So for two sets, a, b, sets of real numbers, and x, just one particular real number, we're going to define how do you do a plus between a real number and a set. You simply take the set of all possible elements of a plus that x. So if this is a number and this is a set, you add them by simply adding this number to every possible element of the set. Similarly, you can define the product as all possible products. If, however, you have two sets, a and b, how do you add them together? Note this isn't a union. I really mean an arithmetic operation of adding. You simply do all possible elements of A and all possible elements of B and add them together. So take all possible sums of elements of A with elements of B. Similarly, all possible products of elements of A and elements of B. So now we can make a whole bunch of statements about sups and infs. Prop 1.2.6, we're going to make those statements now. If you have two sets of real numbers, assume they are both bounded and let x be a real number. The supremum of x plus a is simply x plus the sup of a. That adding of a constant x factors out of taking a sup, as well as taking an inf. As long as x is positive, it also factors out of taking a sup of a product. And it factors out taking an inf. However, if x is negative, you end up with this factoring out of x, but it swaps sups with infs. Because x is negative, multiplication by x will reverse inequalities. So it really changes the role of upper bounds with lower bounds. So that's how we explain this. We will prove it formally. Similarly, if x is negative and you try to factor it out of an inf of x times a, it does factor out, but it swaps it to a sup. The sup of a plus b is simply the sup of a plus the sup of b. The inf of a plus b is the inf of a plus the inf of b. Taking products for sups and infs is a little trickier. And not included in the statement of this proposition, so don't worry about it. Let's prove just item 1. All of the rest are very, very, very similar. So we're specifically claiming that this number equals this number. Okay, these are both two different numbers, that the least upper bound of the set x plus a is equal to the least upper bound of the set a plus the number x. So specifically, we want to show that x plus the supremum of a is an upper bound of the set x plus a, but it is the least possible upper bound. Any number smaller is not. So suppose y belongs to the set x plus a. To belong to the set x plus a means you are of the form x plus something in a. Now what do I know about every element of the set A? Every element of the set A is less than or equal to the supremum. So x plus a must be less than or equal to x plus the sup of a. So y is less than or equal to x plus sup a. This was for any element of the set x plus a. Any element of the set x plus a is less than or equal to this number. That means this number is an upper bound of the set. So the number x plus sup a is an upper bound of the set x plus a. Now we need to show that it's actually the supremum, not just an upper bound, but the smallest possible upper bound. In other words, any number smaller than x plus sup a is not an upper bound. So suppose you pick a number less than x plus sup a. We're going to show that this number b is not an upper bound of the set x plus a. In other words, there is some element of that set which is bigger. So the number x plus sup a is an upper bound. We're now going to show that anything smaller is not. So pick a number b less than x plus sup a. Therefore, b minus x is less than sup a. Now, what was the supremum of a? It's not just an upper bound of a, it's the smallest possible upper bound. Since this is smaller than that, it is not an upper bound of a. So there is something in a which is bigger than b minus x. We now move the x back to the other side, and we find x plus a certain element of the set capital A to be larger than b. But x plus little a is an element of x plus capital A. So this is an element of x plus capital A, it's bigger than b. Therefore, this b is not an upper bound of that set. So what do we have? The number x plus sup a is an upper bound of the set x plus a. However, if you pick any number less than that, it's not an upper bound. So not only is this number, x plus sup a, an upper bound, nothing smaller than it is. That means it is the smallest possible upper bound of the set. It is the supremum. This number is an upper bound of this set, and it is the smallest possible upper bound, so it is the sup of that set. Now that previous proof, I went through in great detail and did, I hope, and did every possible step kind of clearly trying to state what we were doing along the way, because it is a stock standard proof of how you show that a given number is the supremum of a given set. You have a claim that a certain number is the sup of a certain set. First, show that number is an upper bound of the set, but then show anything smaller than it isn't. That is just the default way you show this specific number is the sup of this specific set. Show it's an upper bound, show that anything smaller than it isn't, and then you're done. Okay. Proofs regarding infima are basically the same. Show it is a lower bound and anything bigger than it is not. Now there's a really common error people make stating something regarding strict inequalities with infs and sups. For example, someone might state, suppose A is a subset of the reals, it's bounded below, and every element of A is larger than the number y. Well, if every element of A is larger than y, then so is the infimum. But that's definitely wrong. Consider the set 1 over n, where n ranges through the natural numbers, 1, 1/2, 1/3, 1/4, and so forth. Every element of that set is positive. 1, 1/2, 1/3, 1/4, all positive, all bigger than 0. But we have already shown that the infimum is equal to 0. So even though every element was bigger than 0, the infimum was actually equal to it. However, we will now see that you can make statements with non-strict inequalities. Suppose A and B are two subsets of the reals, they're not empty, and for any element of A and any element of B, the element of A is less than or equal to the element of B. So every element of A is less than or equal to every element of B. Then A is bounded above and B is bounded below, and in fact, the supremum of A is less than or possibly equal to the infimum of B. Let's prove it. Since A isn't empty, there is an X in it. So the assumptions about the sets A and B then state that since this X is less than or equal to every element of B, this X is a lower bound on the set B. Similarly, any particular element of B, and there has to be at least one because we assumed it wasn't empty, must be an upper bound of A. So the supremum of A and the infimum of B both have to exist. They are real numbers. Even better, since every X in the set A is a lower bound on B, the biggest possible lower bound on B is at least as large as any particular lower bound on B. So every element of A is less than or equal to the infimum of B. Therefore, this number, inf of B, is bigger than or equal to every element of A. It's an upper bound on A. So this number, inf of B, is an upper bound on A. But what's the sup of A? It's the least upper bound of A. So if this is an upper bound of A, the least upper bound of A is less than or equal to one particular upper bound of A. So if every element of A is less than or equal to every element of B, not only is A bounded above and B bounded below, but the sup of A is less than or equal to the inf of B. And you cannot prove this with a strict inequality here. Okay, the non-strict inequality, here's the proof. What can we say about sets that are not bounded? When A is not bounded above, for example, the supremum isn't necessarily defined, but it's very convenient to declare what we mean by it. So we're introducing these two symbols, infinity and minus infinity. We're just going to declare that minus infinity is less than positive infinity, and that for any real number, it's in between these two things. This is just kind of like a formal declaration of how this symbol is going to interact with inequalities. Infinity and minus infinity are not numbers. We're not going to do things like arithmetic on them, although we'll see there is a pretty intuitive way to talk about that. We just want to declare how it works with these inequality symbols. So the set of reals combined with these two symbols is often called the extended real numbers, or R with a little star on it. Note that it's not an ordered field. You can't do something like 1 over infinity or infinity times infinity. These are not properly defined for us. But you can do some arithmetic in it. We're just going to declare that if you have a real number and you try to add it to an infinity, it stays the same. Any number plus infinity is still infinity. Any number minus infinity is still minus infinity. As long as x is positive, you can multiply just fine. x times minus infinity would still be minus infinity, and x times infinity would still be infinity. If x is negative, it reverses. A negative number times minus infinity becomes plus infinity, and vice versa. And finally, we can declare some arithmetic with infinities. The sum of two minus infinities is still minus infinity. The sum of two plus infinities is still plus infinity. The product of two minus infinities or the product of two positive infinities is infinity, and the product of two infinities of opposite sign is just minus infinity. But we're not going to try to talk about infinity minus infinity, or 0 times infinity, or infinity over infinity. If you've taken some calculus and you're familiar with L'Hopital's rule, for example, you know that this is a subtler thing than just, yeah, go for it. So we're not going to talk about those operations. Okay. We're actually going to take effort to not talk about the extended reals. It's just a choice that we don't want to have to bring these into play when we don't need to. But it is worth mentioning that a lot of the results that we're going to work with can be restated to include the extended reals in pretty straightforward ways. And it's not a big leap. It's just, as a matter of convenience, when we can avoid talking about the extended reals, we're going to. Okay, and now some definitions regarding these plus or minus infinities. Suppose you have a subset of the reals. If you actually take the empty set, we declare the supremum of the empty set to be minus infinity. If the set is not bounded above, we're going to say that the supremum is infinity. Okay, so we know that by the completeness axiom, if a non-empty set is bounded above, it has a real number that is a supremum. So now we can talk about supremums of the opposite cases. If it's empty, the sup is minus infinity. If it's not empty, but it's also not bounded above, you say that the sup is plus infinity. Similarly, the infimum of the empty set is positive infinity, and if you have a non-empty set that's not bounded below, the infimum is declared to be minus infinity. A word of caution about maxes and mins. So an exercise from section 1.1, a finite set of numbers always has a sup or an inf, which is in the set. So not only does the sup exist, it is an element of that set, similarly for infs. Usually, if the sup or inf of a set is in the set itself, we don't call it a sup or an inf, we call it a max or a min. If the supremum of a set belongs to the set, we call it the max. And if the inf of a set belongs to the set, we call it the min. So specifically, sup and inf always exist for bounded sets. Max and min don't necessarily. Okay, the sup and inf of a set, if it belongs to that set, you call it the max or the min. For example, suppose you take the finite set 1, 2.4, pi, and 100. It's a finite set. It has a sup by that named exercise. The sup belongs to that set. It's actually 100. So since the sup belongs to the set, you call it the max. Similarly, it has a min, 1. And you would therefore technically be correct in writing that the sup is 100, or the inf is 1. But if you know for a fact that the sup is in the set, you usually call it the max, to be clear. But not every set that has a bound has a max or a min. Specifically, you can have a set that's bounded below that doesn't have a minimum. We already saw an example. The inf of the set 1, 1/2, 1/3, 1/4 is 0, but that's not an element of the set. So you can't call it the min. You cannot call it the min if it's not in the set. So if you have a bounded set, completeness axiom tells you it has a sup and an inf. If you know for a fact that they are in the set, go ahead and call them the max and the min. If you know they're not in the set, or you don't know one way or the other, call them the sup and the inf. So let's go over what we've talked about. The real numbers are the only field which contain the rational numbers and are complete. The Archimedean property, very useful result to remember. Make sure to understand how we proved it and how we used the proof in one of our examples. For example, the infimum of 1 over n must be 0. Okay, we proved that and we used the Archimedean property to do so. A lot of arithmetic results involving sup and inf work as expected. They do need to be proved. We only included a proof of one of the many items there. Do recommend, and many of the examples from this section work through others, but you should be able to do them. Arithmetic in the extended real numbers, where you also have this plus or minus infinity, generally works like you would intuitively think. And on a formal level, we simply define it to do so. Just make sure not to do what are called indeterminate forms like infinity minus infinity or infinity over infinity. Those sorts of things you can't properly define, and we don't try. Don't do them.